Welcome to Breadboarding. This is video 26 in the Breadboard 8088 PC series, and this is looking at PC Compatibility Part 4, where we're adding I/O wait states and continuing to test the BIOS. So in the previous video I showed how to build a BIOS compatible with this system that we've been building, but we had a few problems that when I was testing the power on self-test beeps, which uses the 8253 timer, then we came across a problem where the default cycle time was too fast for this particular chip. This particular chip needs an I/O write signal of 400 nanoseconds at least, and we found that the signal by default is only 210 nanoseconds. This was too little time, and so rather than getting the expected 400 Hz signal, we were getting an 18 Hz signal because we were just getting a default 0 or 65536 countdown timer value. So if we have a look at the schematic diagrams that we reviewed a number of videos ago, so this is the original PCXT System 2 clock and control logic. The bit in green down here is the DMA clock, which we did a number of videos ago, but this area up here, which looks quite complicated, is an area that we haven't tackled previously, and this is actually what we're going to need to do to solve this particular problem. The bits in red here are related to the dynamic RAM refresh, so we don't have to worry about that, and there's also an output signal here which is used with the X bus, which we're not actually going to be implementing the X bus in this particular design. So the things in red we don't have to worry about, but all the things in green we are going to need to worry about. And as we briefly covered last time, there are some of the inputs here are related to direct memory access, so DMA controller, so we're going to wire these up, but we're not going to cover the DMA controller in this video. So the bit which is of interest at the top here, we've got a number of signals related to the I/Os and when we're writing and reading to I/O devices. So we've got the I/O read, the I/O write, and the I/O channel ready. If a device needs a bit more time, then if this is held low, it'll extend the I/O access time by a number of clock cycles. And what this circuit does is whenever there is a low on I/O read or I/O write, so whenever we're reading or writing through the I/O, what happens is this output here, which is producing the ready wait signal on the right hand side here. So when this goes high, what this will do, it'll extend the current access by another bus cycle. And in fact, what then happens down here is the output gets fed back round here. And in fact, after one clock cycle, then it actually clears it. So what this effectively does is whenever we're accessing I/O devices, it gives us an extra clock cycle to access the device. Now we're not actually going to implement this particular circuit. What we're going to do is to look at the XI8088, which is what we've been basing a number of elements of the design, because it's kind of a hybrid, includes some aspects of later models like the PC80 and the 386 machines. So this bus arbitration and wait logic is something that we identified we needed to do at some point, and this is what we're now going to do. And in fact, if we look into KiCad, and now found out that KiCad is in fact pronounced KiCad by the team, this is the bus arbitration and wait logic. I have annotated it in a number of areas just for my own understanding. So the key things that we're really looking at here from a input point of view is the I/O side of things is inputting here, and this D-type flip-flop is producing the output here, and the ready wait here is the thing that feeds into the 8284 chip up here. Putting a high signal onto here, this is what will extend the bus cycles and will actually signal the CPU by changing the ready signal. And then the more complicated bit is that this output then feeds into this flip-flop here, is then delayed by the system clock by one bus cycle, and then it comes out of here, and you can see I've got a ready wait plus one clock there. And what that actually does is goes and clears the value from here. So when the I/O read or I/O write goes low, that clocks this flip-flop, will cause this to go high, and then this signal goes round to this flip-flop, and when the next clock signal occurs, then it will actually clock this, and then it basically then clears it. So what this should result in is this signal going high for one clock cycle after the initial I/O read, I/O write, and what that should do is to extend the I/O read, I/O write clock cycle. Then all of these other signals down here are all related to the DMA access, but we'll cover all of those when we talk about the DMA. So what I've done is I have updated our KiCad schematic, sorry. So this is the overall schematic. We've got the processor down on the right hand side here. So this is the processor. We've got the clock controller here, the bus controller down the bottom here. This generates the IO read, IO write and various other signals. And then we have our DMA interrupt controllers and the timer, which is the thing we're actually having problems with as well. I've rearranged things a little bit, and what I've now got is I'm just using a dual flip-flop here. And then what I've done is I've taken the diagram that we had on the previous KiCad page. So the logic for this has been consolidated down. So this is the one of the gates and the flip-flop. This is the other gate and the flip-flop. And all these other gates here and the flip-flops here have all been put into the PLD. So it sort of simplified it quite a bit. And so now what we have here is a lot of the signals are going between the two here. So IO read, IO write is coming in here, and then this produces the IO read write clock signal, which comes in to clear this. So this clocks this particular flip-flop. This produces the ready wait, which goes over all the way to the clock generator. So by putting the ready wait in here, this is what extends the bus cycle. And then the negative output of here is then being fed into the flip-flops here, and we actually get a ready wait +1. So there is just one little complication here in that we're only passing one of the ready wait signals back here. So the output there is the one that goes off down to the clock controller, and that has the inverted ready, whereas we're just actually outputting this one into the PLD here. But in fact, we then need to use the inverted version of that. So the ready is inverted and the wait is positive, but we just handle that in the rules for the PLD down here. So when this circuit is put in and we hook up the ready wait here, most of the DMA ones I'm just going to leave for the moment until we tackle the DMA. But what should happen is our timer over here, which was the thing we had the problems with originally, then what should happen whenever there's an IO read or an IO write, then it should last at least 420 nanoseconds, and therefore we should be able to save the value here. We should then get our 400 Hertz tone coming out of there. In the previous video I did also mention that we'd need to check the minimum times for the interrupt controller and also for the DMA controller, and I have actually gone and checked those data sheets. So this is the programmable interrupt controller, and we can see that the programmable interrupt controller has got a minimum read time of 235 nanoseconds and 290. So that's larger than the 210 nanoseconds that we've got. So the interrupt controllers would certainly have a similar problem to what the timer had. And then if we look at the DMA controller, then the DMA controller has a minimum read width of 200 and write width of 160 nanoseconds. So this probably would have been just about okay, but again it's a little on the boundary here. So it's certainly something that we need to do this before we actually do any further testing and try and do any more testing of the BIOS. So let's take a look at the PLD configuration. So this is the wait DMA PLD, I've called it, and we can see here that we've got the system clock. This is the positive system clock, reset, IO read, IO write. The lock S0 and S1 signals come from the CPU. The HRQ DMA is the request from the DMA controller, so we're not going to worry too much about that. The hold acknowledge is the signal going back to the DMA controller. And again, these DMA wait, AEN, BRD, AEN, ready to DMA, these ones we don't really need to worry too much about. But the inverted ready wait +1 clock cycle, the IO read write clock, and the inverted wait are certainly some inputs and outputs that we need to worry about. So we've got the definitions here. Now normally with a PLD, if you have an inverted input, then generally it's a good idea to actually identify the inverted inputs with an exclamation mark, because then that means that when you're dealing with the logic rules, you only have to worry about a positive logic. You don't have to worry about whether a particular signal like IO read is active low or not. But because of the way how the rules are in the original diagram, so if you look at the rules here, you can see that we've got the S0 bar, S1 bar, that's lock bar, are going into a NAND gate, which is then inverted. So this is an AND. Now, obviously, if we start to take these in as their uninverted values, then this starts to get messy and more likely to make mistakes. So rather than taking the good practice of putting an exclamation mark by all inverted inputs, we're actually going to leave some of these as they were. And these are the comments to the right here just to explain that. Then the outputs, some of these are intermediate outputs that I've defined intermediate outputs just to simplify some of the rules here. And basically now what we have here is if you look at the D1, D2, D3, D4, these refer back to the original flip-flop here. So we look at the D1, D2, D3, D4 and the Q outputs. Now generally all these inputs are going to be reset by the reset signal when it's high, logical high. So the ready wait input here is the input from the other flip-flop, and then this is the line that does the DMA request. So these are the rules that we've got. There's a good chance that there's a mistake in some of these. They are quite complicated, so what we're going to do is to have a look to see whether we get the IO read and write bus cycles extended first, and then after that we can worry about in future videos what the DMA is doing. I'm going to put this board just above where the CPU and the buffers are, and the rest of the DMA IO interrupt controllers are over here. So I've made a new connector here to tie the two boards together, which is then plugged into our power distribution. I will wire some of the power rails together up here in a bit. So this one goes with pin 1 facing downwards, this one pin 1 going up there. So what I'm going to do now is to wire these up, and when we come back hopefully it'll be ready to switch on and see whether or not this resolves our timing issue. So just plug in the chips, just going to put in the power lines and the decoupling capacitors. Then check the schematic, the reset and the clock lines. Just put in the clock feeds into the chips there and reset. Then we need the IO read and IO write, which are actually available at the top of the board up here. So we're just going to take IO read and IO write from there. Now I need to connect the lock S0 and S1 signals down to the CPU for the DMA. Then we're going to be wiring up the right hand side of the flip-flop down to the PLD there for the DMA related signals. Feed into one of the flip-flops for the PLD there. Now we're wiring in all of the IO wait logic between the two chips there. Need pull up to 5 volts. We also need a pull up for the resistor there, and then this is feeding into the controller down the bottom there for the wait states. Okay, so I've finished wiring everything up. There were a few minor mistakes I needed to correct. A couple of connections weren't quite in the right place, but everything seems to be plugged in properly now. So I'm just going to turn on the Nanocomp first of all. And so we've got the Nanocomp 8088 version 3. I'm just going to go load. And what we're going to do is to send down the test program. So you've got test 9, which is the one that we used previously, and we're also going to record the output for the logic analyzer. So this is triggered on the programmable interval timer when that gets first written to. So we're just going to kick that off, going to send our test program down, and then when we run this we should be able to hear beeping sound, and hopefully this beeping sound will be much closer to the 400 Hertz that we expect. We should also see the test pattern on the video card as well. So let's just run it first and see whether or not we've actually got our wider IO read and IO write pulses. That may or may not have come out, but we now have a 400 Hertz tone. Just stop that. And if we have a look at the logic analyzer here, we go into where we've got our programmable interrupt timer and we add some timing markers. So if you now look at how wide these signals are here, so this is where IO read and IO write goes low. If you look over here, they're now actually 625 nanoseconds. So in fact, the circuit that we've added didn't add just one wait state, but it actually added 2 wait states. So have a bit more look at that off video, but basically it's increased the read and write time to the I/O devices sufficient that now we're able to actually store the B6, A6 and 0B, which are the values we need to write to the timer to actually get the 400 Hertz. So that's working okay, and let's just have a quick look at the video capture to see whether we're still getting that okay. You can see here, yep, we've got the colours coming out, so we've got all the characters, we've got all the combinations of colours and attributes. I think I'm going to change the MDA card to default to the green video output, I think, rather than the colour, because it doesn't really look too much like a monochrome display adapter like this. That all looks to be okay, so the only other thing we really need to do now is to download our BIOS again and actually see how far on the power on self-test codes we can actually get. Now I've changed the logic analyzer to be connected to the power on self-test side of the port, so rather than showing the data bus, now it's showing post, and it's now triggered on the post going low. So I'm just going to run the same test program again just to make sure the post port is working. It's now beeping. We zoom in here, we can now see that the power on self-test port should have counting down values from FF all the way down to 1, I think. Should see. So yeah, it looks like the post is working okay. So what that now means is we can download the BIOS again, run the BIOS, and hopefully if there's any problems we should get some beep codes, and we should also get the outputs onto here. Now last time I think we got 1, 2, 3 and 4, so we'll just going to turn this off and turn it back on again just to make sure the RAM is initialized cleanly, and then I'm going to download and run the BIOS. Now before I download the BIOS, I just need to remember to set the extra segment to be 6000, and now I'm going to download the BIOS. It's downloaded. Now I need to set the code segment, code 6000, and now when I go FFF0, then we're just going to run the post monitoring, and now I'm going to hit 0, and hopefully this will start the BIOS up. And we did get a startup tune, so that sounded quite promising. So let's have a look at the logic analyzer. So we do appear to have actually got a little bit further than we did last time. So we've actually got the post codes going down to 08, and we also did get a sound on the speaker, like a startup sound. So you can see we've got the post codes going down to 08, and if we just have a quick look at the source for the error or the post codes, they're not really errors, they're just sort of messages. And in fact, the problem where it stopped is on 8, initialize the keyboard and the keyboard controller. Now, the reason why this won't have worked is because at the moment we haven't got a keyboard and a keyboard controller, so that's perfectly understandable. So I think we can count this as a success so far. So I think we've done enough on the BIOS to ensure that the BIOS is actually starting up. Hopefully once we can add the keyboard controller, or we disable the keyboard controller initialization, we should then be able to get into the video enabling. I'm going to break the video here. We've completed getting the initial BIOS up and running, and we've sorted out the IO8 state. So basically things are coming up and we're hearing beep codes and we're hearing the startup beep. So in the next video we're going to be looking at adding a PS2 compatible keyboard controller, and also look at modifying some of the BIOS code a little bit so we can perhaps test some of the other error messages. So if there's a CPU error, memory error and things like that. And when we add the keyboard as well, then hopefully we'll then be able to get the video controller initializing. We're almost to the stage then we have a functioning PC. So if you don't want to miss out on future videos, please hit subscribe, and if you can hit like, it just helps to make the videos available to a wider number of people. Thanks for watching.